Hello friends, welcome to today's lecture Flexibility Method. Myself Mr. Y.S. Patil, Department of Civil Engineering, Sharad Institute of Technology, College of Engineering, Ketrao. In this lecture, we solve a indeterminate beam by using flexibility method. So let us see one problem. A continuous beam ABC is subjected ABC is fixed at A and simply supported at B and C, such as AB is equal to 4 meter, BC is equal to 3 meter. It is subjected to point load of 10 kN at midspan of BC and span AB carries UDL of 60 kN per meter. Analyze the beam using flexibility method. So this is a given beam, that is ABC at end A is a fixed one and B and C is a simply supported end. The AB span is 4 meter and BC span is 3 meter. On that AB carrying 60 kN per meter UDL and on the BC a point load of 100 kN at the midspan. So basically this is an indeterminate structure because the number of reactions for this particular beam is, for at support A is fixed, means that is 3 unknowns. At support B, that is simple support, means there is 1, and at support C simple support means that 1, that is 3 plus 1 plus 1, that is 5. Number of support reactions become 5, and we know that the number of equilibrium equation becomes 3. So degree of static indeterminacy becomes 2, that is 5 minus 3 is become 2. So for solving this structure, first this structure made by determinate structure. How it determines structure? We remove the support B and support C. So it becomes a cantilever beam subjected to UDL and point load. So this is now determinant structure. Due to that, removing that support B and support C. Then next, this diagram called as M diagram. Then next, we apply B support, that is that B and C becomes now redundant forces. So apply B force or that B reaction at point B. So this is the M1 diagram, and apply at C reaction at point C. This is called as M2 diagram. So displacement due to load in the determinant structure corresponding to redundant, that is form DRL matrix, that matrix due to determinant beam. So DRL1 becomes M into M1 dx upon EI and DRL2 becomes M into M2 dx upon EI. So form a table by using this M diagram and M1 diagram and M2 diagram. So first portion CD. First portion CD, origin C, limits 0 to 1.5. Now in this M diagram, in between C to D there is a no load, means moment in that CD portion at origin C it becomes 0, and M1 in the M1 diagram, this is the D portion, so there is no load, that's why M1 becomes 0, and M2 becomes, that is 1.5 into X. Okay. Then next DB, in between D to B, origin once again remain C and the limits are from point C, that is 1.5 to 3. So with respect to C, moment becomes minus 100 into X minus 1.5. So that X measures from point C. So M is minus 100, X minus 1.5. M1 becomes, means M1 on the at point B. So in between B to D there is no load. So M1 becomes 0 and M2 becomes X. Then next BA. Once again origin consider C. So limits are 3 to 7. Means this 3 to 7 from point C. The M diagram becomes 100 into X minus 1.5 minus, due to that UDL, 60 by 2 x minus 3 bracket square. So M1 becomes, this is the M1 diagram, M1 becomes x minus 3 with respect to this, and M2 becomes x. So this is the table. This, by using this M1 and M2 value, we can form the DRL matrix and flexibility matrix. So first DRL 1, that is integration of M into M1 dx upon EI. So first M into M1, limits are 3 to 7, minus 100 in bracket x minus 1.5 minus 30 x minus 3 bracket square. This is the M, whole equation is M, and M1 is x minus 3 into dx upon EI. By simplifying this equation, we get minus 30x cube minus 10x square plus 420x plus 810 dx upon EI, with the integration limits are 3 to 7. By taking integration for this equation with respect to x, we get minus 30x raised to 4 divided by 4 minus 10x cube divided by 3 plus 420x square divided by 2 plus 810x, with upper limit 7 and lower limit 3. Put up x is equal to 7 for upper limit and put x is equal to 3 for lower limit. Solve this equation, we get DRL1 becomes minus 5253.33 upon EI. Next, DRL2. For DRL2, take the integration M into M2 dx upon EI. For first condition, that is for that CD portion, that limits are 1.5 to 3, minus M is minus 100 into x minus 1.5 and M2 is x dx upon EI, plus for second condition, that is for AC, that is 3 to 7 minus 100 x minus 1.5 minus 60 by 2 x minus 3 bracket square x into dx upon EI. Solving this equation, we got DRL2 is equal to minus 11,654.5 upon EI. So develop flexibility matrix. DRL is equal to, take 1 upon EI is a constant, so the equation becomes 5253.33 and minus 11654.5. This is the DRL matrix. Then next, develop flexibility matrix, F matrix. For that F11, it becomes integration of M1 into M1 dx upon EI. So limits are 3 to 7 x minus 3 bracket square, that is M into M1 dx upon EI. So F11 becomes 21.33 upon EI. So F21 is equal to integration of M1 into M2 dx upon EI. This F21 is equal to, that is F12. So integration of 3 to 7 x minus 3, this is a M1 into x is a M2 into dx upon EI. So F21 is, or F12 is 45.33. Then F22 becomes integration of M2 into M2 dx upon EI. So this is for 3 different parts. So limits are 0 to 1.5 x square dx upon EI plus 1 integration of limits 1.5 to the 3 x square dx upon EI and integration lower limit 3 to 7, that is x square dx upon EI. By solving this equation, we got 1.125 plus 787 plus 0.533 upon EI. So F22 becomes 114.33 EI. So redundant matrix, already we remove the RB support and RC support. That's why redundant forces are RB and RC. So there is R matrix becomes RB and RC. And there is no displacement in the direction of the redundant force. So DR matrix becomes 0. Then the flexibility equation is dr is equal to drl plus f into r. So displacement matrix becomes 0 is equal to 1 upon ei minus 5253.33 minus 11654.5 plus 1 upon ei. This is F matrix, that is 21.33, 45.33, 45.33 and 114.33, and the R matrix, that is RB and RC. Now form a simultaneous equation by using this compatibility equation. First, RB into 21.33 upon ei plus RC into 45.33 ei minus 5253.33 ei. So this is equation number 1. Then next, 45.33 into RB 114.33 RC minus 11,654.5 upon ei. This is equation number 2. So ei is a constant term or constant, so all ei will be cancelled. So this is equation, 2 equations and 2 unknowns. So by simplifying this equation, we get the value of RB and RC, and the value of RB is 118.39 kilonewton and RC becomes 27.54 kilonewton. Now by using this RB and RC, we calculate bending moment. So first, bending moment at C is 0 because the bed simply supported ends. Then bending moment at B, so bending moment at B is 27.24 into 3 and minus 100 into 5, 1.5, so it becomes minus 67.68 kilonewton. Then bending moment at A is 27.24, that is RC into 7 minus 100 into 1.5, then 188.39 into 4, that is RB, and minus 60 into 4 into 4 by 2. So bending moment at A becomes minus 84.39. These are the support moments. Then calculate the free moment. Free moment for simply supported beam carries a UDL over entire span. The maximum bending moment becomes WL square by 8, that is 120 kilonewton meter, and a beam is carrying a point load at the midspan, that is WL by 4 for maximum bending moment, and the value becomes 75 kilonewton meter. So first draw the free bending moment diagram for this AP and BC portion, and these are the positive value. Then draw bending support moment, that is at point C0, at point B 67.68 and at point A 84.36. These negative values. So join all points. The overlap with free BM with support moment, that we cancel, and this is the baseline. Above the baseline bending moment value is positive, below the baseline bending moment value is a negative. So this is the final BMD for given beam. Thank you.